All right. Greetings, YouTube. Beautiful Mind here, and we're going to continue our exploration. We're going to culminate our exploration of Chapter 4 on trigonometric functions with Section 4.8 on sum and difference formulas. A few objectives. 1, use the sum and difference formulas for cosine. 2, use cofunction identities. 3, use the sum and difference formulas for sine. 4, use the sum and difference formulas for tangent. 5, use double angle formulas. 6, use power reducing formulas. And 7, use half angle formulas. So here we have some sum and difference formulas for cosine. Cosine of u plus v equals the cosine of u, cosine of v minus the sine u sine v. Okay, let me see. So for again, cosine u plus v is cosine u cosine v minus sine u sine v. Cosine of u minus v is cosine u cosine v plus sine u sine v. Okay. So sum and difference formulas for cosine. Okay. So double cosine, and the signs are opposite. So if we have u plus v, it's double cosine. It's cosine u cosine v minus sine u sine v. And then if we have the cosine of u minus v, it's the double cosine, but then it becomes plus. Okay. All right, let's see it in action. So here we're asked to find the exact value of, we have the cosine of pi over 12 by using the notion that pi over 12 equals pi over 3 minus pi over 4. Okay, let's see if we can do this. We should be able to do this one. So I don't know that I'm necessarily going to draw out the unit circle right now, but on your end, it's a good idea. We're going to be using a unit circle here, or at least I am. All right, so, maybe if we kind of talked about how to construct the quadrant 1 of the unit circle, right? So just kind of be cognizant of that. So, okay, again, if we want to find the cosine of pi over 12, okay? Now, we're told that to use the fact that pi over 12 can be rewritten as pi over 3 minus pi over 4. So there's going to be the cosine of pi over 3 minus pi over 4, okay? So then if we apply the difference rule for cosines, it should be cosine u cosine v plus sine u sine v, okay? So it should be cosine pi over 3 times the cosine of pi over 4 plus sine of pi over 3 times the sine of pi over 4, okay? So then pi over 3 is 60 degrees, right? So if we use the unit circle, right? Cosine of there, it should be a half. So cosine of pi over 3 should be a half. Pi over 4 should be root 2 over 2. Okay. Plus sine of pi over 3. So it should be root 3 over 2 from the unit circle. And sine of pi over 4 should be root 2 over 2, also from the unit circle. Okay. That looks pretty good. So it looks like I'm getting root 2 plus, I think it's root 6 all over 4. Okay. So I think we can, let's see if we can verify this with the calculator. Okay, we got our exact result. So let's make sure we're in radians. We are. Let's do the cosine of pi over 12. We get an answer, okay? So then let's put in our exact answer that we got. We got the square root of 2 plus the square root of 6. Close off that numerator, divided by 4. We should get the same decimal, and we do, okay? So we can be confident in that result. Okay. And here's a type version of what we just experienced. Cosine of pi over 12 is cosine of pi over 3 minus pi over 4. So we apply the difference formula for cosine, cosine to the power of 3, cosine to the power of 4, plus sine to the power of 3, sine to the power of 4. I think those are good, and we got the same result. Okay. So basic cofunction identities. If v is any real number or angle measured in radians, then the cosine of pi over 2 minus v is going to be equal to the sine of v. And the sine of pi over 2 minus v equals the cosine of v. Okay. If any angle v is measured in degrees, then replace pi over 2 with 90 degrees in these identities. Okay. So cofunction identities. All right. The cofunction for sine is cosine and vice versa because of this property. Okay. So we want to prove that for any real number x, the tan of pi over 2 minus x equals cotan. Okay. So let's start with what we're given. And we got the tan of what? Pi over 2 minus x. Again, we're taking the tan of that guy. Okay. So tan is what? Sine over cosine. So I'm going to do, we're going to do our sine over our cosine. Again, this is what? Sine of that. This is cosine of that. All right, so tan of pi over 2 minus x means sine of pi over 2 minus x over cosine, all right, of pi over 2 minus x, okay? Sine of pi over 2 minus x is what? That's cosine from the cofunction property or identity. So that should be the cosine of x over the sine of x. This is cotan of x. Okay. Here's a type version of what we just experienced. Tan of pi over 2 minus x is sine over cosine, but sine of pi over 2 minus x is cosine, and cosine of pi over 2 minus x is sine. Cosine over sine is cotan. Okay. So then we have sum of difference formulas for sine. All right. So then when we say the sine of u minus v, so now when we did cosine of u minus v, it was a double cosine and the signs change. Now for sine of u minus v, it's sine u cosine v. The sign stays the same. Then we say cosine u sine v. So it goes sine cosine and then cosine sine. Okay. Similar for the sum formula for sine. Okay. So find the exact value of this guy without using a calculator. Okay. So we have what? The sine of 63 degrees times the cosine of 27 degrees plus the cosine of 63 degrees times the sine of 27 degrees. Okay. That looks like the sum formula for sine. So that looks like the sine of 63 degrees plus 27 degrees, 80, 90. Sine of 90 degrees. So on the unit circle, when we're at 90 degrees, the order pair is what? 0, 1. So sine is 1 at 90 degrees. Okay, so far so good. Okay, and let's compare this to our prepared notes. So this expression is the right side of the sum formula for sine of u plus v, where u is 63 and v is 27. So what we did was they pretty much did the same thing we did. It condenses down to sine of 90, which is 1. Okay. So then we have sum and difference formula for tangent. If we wanted the tan of u minus v, so if we took what? If tan is sine over cosine, we could do sine of u minus v over cosine of u minus v, and then through our algebraic manipulations and trig identities, we can ultimately get to here. Okay. More than likely, that's what I'll do. I probably won't commit this to memory. I'll probably just use the sum and difference formulas for sine and cosine. But if we wanted to be more concise, just use these formulas. I just like my twofers. I like it when I get multiple things from just knowing a few things, right? So we want to verify this. So we could just use the sum of difference formulas for tan like we saw on the previous slide. I just feel inclined to use my sine and cosine. So I just want to see if I can do that. That's going to probably be a little bit worse because we're introducing more variables as opposed to just using the formula directly. But that's just my prerogative, right? So that's your business, right? The tan of pi minus x. Okay. So I just want to see. Let's do sine of pi minus x over cosine of pi minus x, okay? So if we apply the difference rule for sine, that should be what? The sine of pi times the cosine of x minus the cosine of pi times the sine of x, okay? And then the difference rule for cosine, this is going to be cosine pi cosine x plus sine pi sine x. Okay? Let's see. Okay, what's the sine of pi? I think that's 0, right? The y value, yeah. So this term collapses to 0. What's the cosine of pi? Is that -1? Mm-hmm. So then on that second term, it's like we have a double negative at play. We have our original negative. The cosine of pi is what? -1. So then ultimately that collapses down to just sine of x. Okay, so I'll just put it here for now. I'll move it as needed. Now for the denominator, cosine of pi, right? -1. So this guy is -1. Sine of pi is 0. Looks like this collapses to 0. Okay. So it looks like we have sine of x over a negative cosine of x. Sine over cosine is tan. We get our desired result of a negative tan of x. Okay. We started with the left, we finished with the right. Okay. Now let's see. Maybe the book used the difference rule for tan. Let's see the way the book did it. So they applied the difference formula, right? That's fine. Tan of pi. Sine is what? 0. Yeah. Okay. So eventually they got to the same thing that we did. It just makes more sense for me in terms of sine and cosine. But yeah, this is fine. Let's keep moving. So if cosine of theta is -3/5 and theta is in quadrant 2, okay, find the exact value of each expression. Okay, so let's apply those. I got some I need some copies. 1, 2, 3. Okay, let's do 2 more copies of this. Let's duplicate and do another copy. So 1 for each one, A, B, and C. Okay. All right. Okay. So what we have, cosine of theta equals a -3/5. So before I do the other items, can we do what? Sine squared theta plus cosine squared theta equals 1. Let's see if this works. So then from there, sine squared theta, we got this plus this -3/5 squared equals 1. So then sine squared theta, that's a 9/25. 15, so 16/25. Okay, so we get that sine of theta. Right now we're getting plus or minus 4/5, because when you take the square root, do plus or minus. If we're in quadrant 2, sine corresponds to our y. Y is positive in quadrant 2. So I'm just going to take the positive value because we're in quadrant 2. Okay. So our claim is that what? we have this cosine of theta equals a negative 3 over 5. And then sine of theta equals like 4 over 5. Okay? Okay? So then if we're working A, I'll just start A here. If we're considering what the sine of 2 theta, I'm going to write this as the sine of theta plus theta. Okay? Does this help us? Let's keep going. All right? So then if we apply our sum formula, okay, so that should be what? The sine of theta times the cosine of theta plus cosine theta sine theta, right? Something plus itself becomes double, so I'm just going to condense that down. There should be 2 sine theta cosine theta, okay? And then I think we found those components. So it should be 2 times sine of theta, we got 4 over 5. Cosine of theta, negative 3 over 5. 8 times 3 is what, 24? So I'm getting a negative 24 over 25 for that one. That's for A. Okay. All right, we're going to go with it. Cosine of 2 theta. Let me get a copy of this. Okay. Let me go ahead and paste it here as well. Okay. So then for B. So if we're doing cosine of 2 theta, that means what? Cosine of theta plus theta. That means what? Cosine theta minus sine theta, okay? We can condense that down. What is that? Cosine squared theta minus sine squared theta. Okay, so for cosine, we got this negative 3 over 5 squared. Sine, we got 4 over 5 squared. 9 over 25 minus 16 over 25. Negative 7 over 25. Maybe I can fit C. I'll just go ahead and do C on the next slide. Okay. So then for C, we have what? The tan of 2 theta. That maybe we can do what? The sine of 2 theta over the cosine of 2 theta. So for sine, we got a negative 24 over 25. For cosine of 2 theta, negative 7 over 25. So then ultimately there we get a positive 24 over 7. Okay. Let's get rid of that. Okay, let's see, how do we do? Oof. Okay. Okay, so for sine, so use identities to find sine and tan. Sine, 4 over 5, tan. I don't think we found tan, but that's fine. For A, the negative 24 over 25. B was negative 7 over 25. And then C was a positive 24 over 7. I think we got the same results, okay? So again, for C, they used the sum rule for tan, you know. We just use sine over cosine. Okay. So then we have these power reducing formulas. Sine squared reduces to, or is the same as 1 minus the cosine of 2x over 2. Cosine squared is the same as 1 plus cosine of 2x over 2. And tan squared is going to be 1 minus cosine of 2x over 1 plus cosine of 2x. Okay. Okay, let's keep going. What's going on here? Why does that look like that? Oh, it's just not at the top. Okay. So here we're asked to write an equivalent expression for cosine to the 4 of x that contains only first powers. So we want to use those power reducing formulas. Let me see. We got this cosine to the 4 of x. Let me see here. Cosine times cosine. Cosine, we just said in the previous, let me see something. Right there. So cosine of 2 theta is cosine squared minus sine squared. So cosine of 2 theta plus sine squared. Hang on, I'm just trying to see something. Sine squared two theta. Okay, it's there. I think I'm trying to derive this guy, right? Cosine squared okay, so for instance, if we're looking at this double angle formula for cosine, we got what? Cosine squared minus sine squared. So if we solve for cosine squared, add the sine squared to both sides, we get cosine of 2 theta plus sine squared. Does that help us? 1 minus cosine squared. Okay, I think it does, right? So look, I'll just do it here, I guess. So we got this what? We got that cosine of 2 theta equals cosine squared minus sine squared, right? So suppose we solve for cosine squared from b, all right? So if we solve for cosine squared, we're going to have what? Cosine squared theta is going to be equal to the cosine of 2 theta plus sine squared theta, right? Okay. So now sine squared is the same as what? From Pythagorean theorem, sine squared plus cosine squared equals 1. So we can rewrite sine squared in the following way. So this first part just persists. Sine squared is going to be what? 1 minus cosine squared theta, okay? We can add that cosine squared to both sides. So then we'll have 2 cosine squared theta equals cosine of 2 theta plus 1. Divide both sides by 2. I'm just out of space. So then we get cosine squared theta equals cosine of 2 theta plus 1 all over 2. And if we fast forward, cosine of 2 theta plus 1 all over 2, right? So using the double angle formulas and the trig identity, that's where these guys came from. That's why I was pausing and hesitating, because I was like, I think we can derive these guys. And it wasn't too terribly bad, right? We see it here in purple. I think I'm going to shrink it down just a little bit. And then reposition it. I'm going to get rid of this. And then resize this. Or I'll cut it and I'll move it to next to this guy, paste. And so the same way how we just did this for cosine squared, we derived the power reducing formula for cosine squared. I'm sure it's something similar for sine and tan. Okay. Okay, that's fine. That's why I was pausing. I was like, wait a minute, I think we can do this derivation. So I was just doing it on the fly. Okay. All right. So here, what we're going to do, cosine to the 4, we're going to rewrite it as cosine squared x, quantity squared. So we just said that cosine squared is the same as 1 plus cosine of 2x all over 2, and then that is quantity squared, right? So now if we square that, the top becomes what? A 1 plus 2 cosine of 2x plus cosine squared of 2x all over 4, okay? Our goal is we want to write an equivalent expression for cosine to the 4 that contains only first powers of cosines of multiple angles, okay? So we need to do that cosine squared again, okay? So we're still going to have this 1 plus 2 cosine of 2x, and then cosine squared is going to become okay, let me see. So this guy, 1 plus it should be cosine, I guess it's going to be cosine of 4x over 2. Okay, and then we still have this over 4 here. Okay, so I'm going to multiply by the reciprocal. So I'm going to distribute a 1/4. I'm getting 1 over 4 plus a half cosine of 2x okay, I'm getting a, if we, let me see, we're multiplying by 1 over 4. I'm getting a plus of 1 over 8. And then plus 1 over 8 times the cosine of 4x. Okay, we need to do one more. 2 over 8, so that becomes a 3 over 8. I'm getting 3 over 8 plus 1/2 cosine of 2x plus 1/8 of cosine of 4x. Okay, let's compare this to our prepared notes. Let's see, did we get catch all the nuances? Okay, let's see. So they wrote the square, they changed from cosine to the 4 to cosine squared squared. Applying the power reducing formula, the cosine squared becomes 1 plus cosine of 2x over 2. Then you square that, so you get a 4th 1 plus 2 cosine of 2x plus cosine squared of 2x. We got all that. Then they apply the power reducing formula again. They have the 1 plus cosine of 4x over 2. Okay, then they brought that 1/2 up, so that was a half plus a half times that. Distribute the 4th, and I think we got the same thing. 3 over 8 plus a half cosine of 2x plus 1/8. Right? 3 over 8 plus a half cosine of 2x plus 1/8. Yeah, we got the same thing. Okay, so just do your best to be neat and organized and just try to keep track of everything. That's the main takeaway there. Take your time, you know. Okay, so then we have half angle formulas. So we did some double angle formulas. So then the sine of theta over 2 plus or minus, I'm sure these come from the double angle formulas. The sign plus or minus depends on the quadrant in which theta over 2 lies in. Okay. Then we got an example. Verify this identity. Let me think. Missing a slide. It just didn't register. Okay, that's fine. Verify the identity. Let me see. Sine of x. Okay. Double angle, half angle formulas. Let me see. Replace x with what? X over 2, let me think. I'm gonna look at my notes real quick. Replace this in the double angle identity. Okay, so let's do that. So the recommendation was to replace x with x over 2 in the double angle formula identity, all right? So this looks like what? Let's look at the double angle formula for sine, right? So we'll start here. If we had the sine of x plus x, right? That would be, long story short, it should be 2 times the sine of x cosine of x. Okay, I think that's good. So then the recommendation is to replace x with x over 2 and this guy. So let's just do that and see what happens, right? So then if we replace x with x over 2, we'll have what? Sine of x over 2 plus x over 2 should equal 2 times the sine of x over 2 times the cosine of x over 2, half angle formulas. So we probably need to apply the half angle formulas. Sine of x so on the left we have sine of x okay. So like for instance here, if x over 2 plus x over 2, that's just what? The sine of x equals 2 times the sine of x over 2 times the cosine of x over 2. Okay, let's keep going. Sine of x, okay. So what if we plug this in there? That's cosine squared. Okay. So now based on this property, let's take this and plug this into that left-hand side, all right? So if sine of x equals this, then the following should be the case. We have this 2 times the sine of x over 2 cosine of x over 2 times another cosine of x over 2. I just took this above line and plugged it into the left-hand side, okay? So we're almost there. Okay, sine of x equals all of that, okay? So we said we plugged in, so that's the left-hand side equals this, okay. So then from here, this gives us what? 2 times the sine of x over 2. And it looks like we got a cosine, right? Cosine squared of x over 2. Which is what? 1 minus sine. Do we need to use the power reducing formulas? Cosine squared is 1 minus sine squared. What's the power reducing formula there? I don't remember it. Is that it there? No. Or we could use this. Well, I'm going to try the power reducing formula. I probably should use the formula on the previous slide. 1 plus cosine of 2x over 2, right? 1 plus cosine of 2x over 2, okay. So I'm going to let this be, we said what? 1 plus cosine of 2x over 2. but our x in this case is x over 2. Okay. So then these are going to cancel. Okay. We got cosine of x. Okay. And then it looks like these are going to cancel. And we are going to be left with sine of x over 2. There's a, okay, so that's a 1. Oh, there it is right there. That's exactly what we want. Times 1 plus cosine of x. What an adventure, right? So we eventually got there. Okay. So let's do a quick recap, and then we'll compare it to the prepared notes. All right. So the hint that we started with was replace x with x over 2 in the double angle formula, right? So first we started with the double angle formula for sine. Sine of 2x is ultimately going to be 2 sine x cosine x, okay? So then what we did, we replaced the x with x over 2. So then on the right-hand side, we replaced the x's there with x over 2, okay? So now on the left, a half plus a half is a whole, so that's where we got this sine of x. On the right, we just brought it down at that moment. So now we got an expression for sine, all right? We're saying that sine is this 2 sine x over 2 cosine x over 2. So then what I did, I took this expression for sine and plugged it into the left-hand side. So I just replaced this guy with this guy, and that's where this came from, okay? So then we had 2 sine x over 2 cosine x over 2 times this additional x over 2, which shows up here, cosine x over 2, okay? So then it became cosine squared, right? And then we used the power reducing formula. So the cosine squared became 1 plus cosine of 2x over 2. But our x is x over 2 in this case. So it's a little bit, I know it's a lot of x's over 2's at play, but that's what it was, right? So then these 2's canceled. This 2 was canceled by this 2. And we were left with sine of x over 2 times 1 plus cosine of x. That was fun. Let's compare this to the prepared notes. So replace x with x over 2 in the double angle identity. So in the double angle identity, we had sine of 2x equals 2 sine x cosine x. So then if we replace x with x over 2, on the left we're going to have sine of x. On the right we're going to have 2 sine x over 2 times cosine x over 2. We got to that point. So then what we did next is we took this guy and plugged it in right here on the left-hand side. All right, let's see if that's what they did. And indeed, that's what they did. You can see it here in red. Then we had the cosine squared. Then we used the power reducing formula, 1 plus cosine of 2x over 2. But again, our x is this guy here, right? Then these guys cancel. This is canceled by this. And we're left with our desired result. So they pretty much did the exact same thing that we did, right? All right, gentlemen. Okay, and I think that is it for us. I'm going to add a page here. And so with that, we're going to go ahead and end the session here. And from one beautiful mind to another, take care and peace.